This is Dr. N. Ramya, Assistant Professor from Civil Engineering Department. Today my topic is on resistance to flow of fluid in smooth and rough pipes in hydraulic engineering. So here the resistance of flow of fluid in smooth and rough pipes. So this is what a resistance of flow. When a fluid is flowing in a pipe, due to the roughness, due to the pipe boundary, due to the solid, there is some resistance offered to the flow. There is some resistance offered to the flow in a pipe. Offered to a flow in a pipe. So here, how this flow is resisting in smooth and rough pipes, now we are going to see, right? In pipe, in previous sessions also we have discussed that in a pipe there is two types of flows are flowing. The one is laminar flow and other is a turbulent flow, right? Laminar and turbulent flow. These two are differentiated by a Reynolds number, right? If the Reynolds number is less than 2000, then we are calling it as a laminar flow, and if the Reynolds number is greater than 4000, we are calling it as a turbulent flow, right? So depending upon the Reynolds number, we are differentiating two types of flows, and that flows are moving in a closed conduct, in a pipe, right? So due to the boundaries, whatever the resistance is offering to the flow inside a pipe is mainly of a boundaries, right? Boundary of the pipe. If the pipe has a smooth boundary, then there is a rest resistance to the flow. If it is a very rough boundary, rough pipe, rough solid body of the pipe, then the resistance is more, right? So depending upon your pipe, also there is a resisting offered. Is it more or is it less, right? So these resistance is due to the friction. The resistance is due to the friction. It is caused between the fluid layers and between the fluid and pipe wall. Between the fluid and pipe wall. The friction is coming into picture between the fluid layers and also between the fluids and pipe walls. Mainly because of the frictional resistance is offering the flow to resist the flow at the boundaries. As we all discussed that due to the resistance offered by the boundaries, there is a velocity is 0, and at the boundaries the velocity is 0. At the center the velocity is maximum, right? In laminar flow we have seen this, right? And also in turbulent flow also, right? At boundaries, this is a turbulent flow velocity profile, and this is for laminar flow velocity profile. So here at boundaries, for what type of flow is in a pipe, at the boundaries the velocity is completely a 0, very minimum, that is a 0, because of the frictional resistance, offered by the boundaries, by the solid walls, right? This is what a frictional resistance is. Due to this, there we are seeing a velocity completely a 0, and velocity as we are moving upwards, from the boundaries and away from the boundaries, we are seeing the maximum velocity, because as we are moving further, there the resistance power is getting reduced, right? These at these boundaries, the resistance power, the velocity is zero, complete resistance power. As we are moving away from these boundaries, there we are seeing increase in a velocity profile, right? This is what a velocity diagram is for a laminar flow, right? This is what a velocity profile is. At boundaries, the velocity is zero. As we are moving away from these boundaries, at one point there is no resistance offering by the frictional resistance. Then there we are seeing a velocity is a maximum velocity, right? This is what a frictional resistance causing the flow to slow down, resisting the flow in a closed conduct, right? So it impacts pressure drop, head loss, energy consumption, right? Head loss is maximum for rough pipes and minimum for smooth pipes because of the frictional resistance, and there is a pressure drop, and also energy consumption is also more for rough pipes because of the resistance offering is more for the rough pipes, right? Behavior differs in both smooth and rough pipes, how we see now, right? So here fluid experience resistance as they move along the internal pipe surface. As the fluid is moving inside the pipe surface, there we see some frictional resistance due to the pipe surface, right? And these mainly depending upon some factors. Those factors are first viscosity, right? If viscosity is more, if viscosity is more than the movement, than the velocity, let us say this is viscosity and here is the velocity is less. If velocity is less, this we have seen the condition that the flow is laminar flow. There is less resistance, and here we are seeing a velocity profile is parabolic, and also the energy loss is less when comparing with the turbulent flows, right? If viscosity is high, laminar flow, right? If viscosity is less, therefore the velocity is high. The viscosity is less and velocity is high, then the flow is turbulent flow, and the energy loss is also more because of the formation of the eddies and vortices in the turbulent flow, right? So main first factor is the viscosity factor, right? And other is a pipe surface. If the pipe surface is smooth, then less resistance. If pipe surface is rough, there is more resistance power, right? So here, here be depending upon the surfaces also, there is a change in a flow, that is whether it is laminar or turbulent because of the flow type. Flow type. We may also vary a type of flow moving in a rough pipe, and the velocity of the fluid. If velocity is more, then turbulent flow, velocity is less, laminar flow, and depending upon this resistance also, velocity plays an important factor for assisting a flow, right? And pipe dimensions. Pipe dimension is also a one factor of resistance of the flow in a different pipes. And it is very important to know for hydraulic and industrial piping system. It is very important to estimate the resistance, how much resistance is occurring in a pipe, so that the external energy we have to give to the flow. Some additional power is required, some additional energy is required to overcome the resistance in a pipe. So here the types of pipe surfaces are a smooth pipe. So this is what a smooth pipe diagram is. Smooth pipe, the flow is also moving in their own paths. So here the smooth pipe means the interior surface is very neatly polished and minimally rough. It is very smooth polished and less, very less rough. And resistance mainly depend upon your viscosity. As I said you, depending upon the viscosity, there is a change in a flow type in a closed pipe. So here rough surface, here due to the irregularity in boundaries of the pipe, the flow is also getting changed. The irregularities and projection of internal surface resistance is due to both viscosity and also surface roughness. There is resistance. It is due to a viscosity and also because of the surface roughness in a pipe. Here the types of flows in a pipe are a laminar flow. All fluid particles will move in their own paths without disturbing the other particle. It is moving in their own paths in a streamlines, right? Streamlines. And here the Reynolds number is less than 2000. The Reynolds number is what? Inertia force by viscous force, and inertia force is what? Rho Vd by mu is your Reynolds number, dimensional as unit is the Reynolds number, right? This is what a Reynolds number formula is, mu. If it is less than 2000, then it is a laminar flow. In our turbulent flow, it is having irregular mixing, and it is because of the high velocities, because of the low viscosity of the fluid, because of the high velocity, the particle may not move in their own path. It starts stifling to one part to the other part, and it is start moving from one to other, then we see a zigzag, a flow, irregular pattern, and there is a particle layer mixing, adjacent layer moving to adjacent layer, and it is irregularly mixing, and there is a formation of, because of the particle moving from one to other part, we are seeing a formation of eddies or vortices, right? Due to these eddies, the energy loss is also more high in turbulent flows, high in turbulent flows. And this is also resistance. Reynolds number should be having greater than 4000. This is what a turbulent flow is, and the resistance offered by the both viscosity and also due to the roughness of the pipe surface. And here this frictional factor, this frictional resistance is have the equation which is derived by Darcy-Weisbach, and this equation we call as a Darcy-Weisbach equation, right? This is what HF is equal to 4F LV square by 2GD. This is what Darcy-Weisbach equation is for head loss due to the friction. Head loss due to the friction equation is 4FLV square by 2GD, right? So here the term F is a Darcy friction factor, and L is the length of the pipe. L is what? A length of the pipe, and D is the diameter of the pipe, right? And velocity is with what velocity the fluid is moving inside the pipe velocity, and G is the acceleration due to gravity, right? 9.81 meter per second square. We take this is G is your acceleration due to gravity. So depending upon all these there is an equation. It is very important to find the head loss due to the friction. That is what FLV square by 2GD. Here F into LV square by 2G. Correct? Both equations are same. FLV square by 2GD. Right? This is what our equation is. Right? 4FL V square by 2GD. This is what a friction factor. For here, two types of flows we are seeing in a pipe. One is laminar and turbulent. And here also we are seeing a Reynolds number. And one more thing is coming into picture, that is what? A relative roughness. Depending upon both these Reynolds number and also roughness, relative, we call here as relative roughness, that is K by D. Due to this, depending upon these two, there is a friction factor F. Friction factor F is, for laminar flow directly, the friction factor is 64 by Reynolds number. 64 by Reynolds number for laminar flow. If it is a laminar flow, then the friction factor F is 63 by Reynolds number. Now coming to a turbulent flow determined from Moody's diagram are empirical formulas. Why? This turbulent flow is very complex one. As we discussed, right, due to this complexity, we calculate the friction factor F by using a Moody's diagram. By using a Moody's diagram or by empirical formulas, right? And in further, we discuss what is Moody's diagram is. Turbulent flows, resistance in smooth pipe, resistance influenced by viscosity and minor surface roughnesses, and friction factor decreases as Reynolds number increases. So friction factor, just now we have seen that 64 by RE is for Reynolds number. Here is the formula, right? So if Reynolds number is getting decreased, then your friction factor will start getting increased, because both are inversely proportional to each other, right? For each other, inversely proportional to each other. If the Reynolds number is getting reduced, then your friction factor will start increasing. If Reynolds number is getting decreased, then your friction factor will start increasing. If Reynolds number is getting increased, then your friction factor starts decreasing. Right? This is how the both relationship, the friction factor and Reynolds number is. F is inversely proportional to Reynolds number for smooth pipes. This is directly proportional to viscosity. Right? And F is directly proportional to viscosity, because the Reynolds number is rho V D by mu. So here this rho will go upside, F is equal to mu by rho V D. Right? Because this is directly proportional to viscosity. Clear? It is the resistance in rough pipes. In laminar flow, roughness has negligible effect. In laminar flow, roughness has very negligible effect. We can neglect it. In turbulent flows, resistance depending upon the roughness height. Here relative roughness, just now we have seen, right? Relative roughness. Resistance depending upon mainly the roughness and also the diameter of the pipe, K and D. K and D. So friction factor becomes constant beyond a critical roughness. Beyond the critical roughness, F will become a constant. F will become a constant, right? So the higher head loss observed compared to the smooth pipes. This is having turbulent flow, is having higher head loss. As we said that energy loss is more for turbulent flows. That is what here is. And also it is for rough pipes also, energy loss is more when comparing with the smooth pipes. So here are the formulas to find out a friction factor F. To find out friction factor F, if it is laminar flow, then the formula is 64 by Reynolds number. 64 by Reynolds number. The smooth pipe turbulent flow, because when velocity is high, then the turbulent flow in a pipe, then the friction factor is 0.316 by Reynolds number to the power of 1 by 4. Right? This is what a equation for turbulent flows. And completely turbulent flows, that F is equal to 1.14. If completely turbulent flow, then friction factor is 1.14 plus 2 log to the power of log 10 D by E all to the power of minus 2. This is for complete turbulent flow. And here, One more thing, transitional region. Transitional region is when flow is getting transmitted from a laminar to turbulent flows. The small state that we call as a transitional state. This region we call a transitional region. So transitional region formula friction factor is, this is the friction factor, minus 2 log 10 E by D by 3.7 plus 2.51 by Reynolds number F to the power of 1 by 2 whole to the power of minus 2. This is what a transitional region formula for friction factor. And here the resistance to the flow in smooth and rough, what are the parameters we see now? Laminar flow mainly depends upon the viscosity, as same as in smooth. Right, here also roughness, in roughness also viscosity plays an important role, viscosity and as well as velocity in rough pipes, right? Turbulent flows, Reynolds number, roughness effect, both. Less roughness effect. Here depends on Reynolds number and roughness. Both here also, both depends upon roughness and also Reynolds number. Friction factor. Friction factor is what? Is lower for smooth pipe. Friction factor is high for rough pipes. Friction factor is low for smooth pipes and it is high for rough pipes. Head loss is low, less for smooth pipe. Head loss is high for rough pipes. Applications is laboratory, precise equipments, and here municipal and industrial pipeline. The roughness pipes. Applications. Roughness pipes is used for municipal and industrial pipelines, and in this laboratory and precise equipment, these are what applications for smooth and rough pipes. Applications: municipal water supply and drainage systems, oil and gas pipelines, industrial fluid transport systems, and HVAC firefighting networks, and accurate friction factor prediction essential for efficient pipeline designs. These are all applications for the smooth and rough pipes, which is offering a resistance to the flow. Now here Moody's diagram. Just now we have seen the turbulent flows. To calculate the friction factor, we require empirical equations or Moody's diagram. Right? So what is Moody's diagram? Now we are saying it is a graphical representation to find out the friction factor against the Reynolds number and also relative roughness. So depending upon these three factors, we can find out the friction factor. Depending upon these Reynolds number and relative roughness, we can find out the friction factor by using a Moody's diagram. It is a graphical representation. So it is important to determine flow regime, head loss in some engineering applications. And it shows the behavior of the fluid flow in rough and smooth pipe distinguishingly, right? This is what a Moody's diagram is. Friction factor on y-axis, and on x-axis it is Reynolds number. It is Reynolds number, and here is what? Relative roughness. Here is what? A relative roughness. By seeing this relative roughness and by Reynolds number, if let us say if 0.0004 is relative roughness, and if the flow is Reynolds number is having a 10 to the power 5, so I am drawing, yes, at this point, this is what a friction factor is, 0.016. Yes, this is how we plot a friction factor using Moody's diagram, right? By taking Reynolds relative roughness and also Reynolds number, we can find out a friction factor. This is how we are finding. Let us take it is 0.2 and it is 0 10 to the power of 7. Let us take. So this is how you can plot. So this is what F is equal to 0.048. This is how we calculate, we take a friction factor. Right? This is what a laminar flow friction factor is. Right? The graphical representation between the friction pipe and relative roughness. See, relative roughness is K by D. That's friction factor can be calculated by using Reynolds number, and also relative roughness. It is essential to find out the head loss in different flow conditions. Right? Axis of Moody's diagram. Here in x-axis it is Reynolds number. In y-axis it is friction factor, and multiple curves each represent a different relative roughness, that is K by D, right? Relative roughness, and the smooth pipe shown by a single curve in a diagram, right? So as already we discussed, the if you have seen the laminar flow is having a straight line on left hand side, the friction factor is 64 by RE, and the transition zone is 2000 to 4000. In between these, the state we call as a transitional zone, right? It is unstable and unpredictable region, the small transitional state is, and friction factor varies irregularities, right? Friction factors may see irregularities. And here the turbulent flow is greater than 4000. The curved lines on the right, this is what a curved lines are, right? Curved lines, relative velocity, relative roughness, sorry, relative roughness K by D. Depending upon these both Reynolds number and relative roughness, we can find out a friction factor. Clear? This is how we use a Moody's diagram, calculating the Reynolds number first, and after the determining the relative roughness. First calculating the Reynolds number, and after that calculating the relative roughness K by D, and after locating the Reynolds number on x-axis, locating the Reynolds number on x-axis, and more vertical to intersect the curve K by D, and you can corresponding to the friction factor on y-axis. This is how we have done. I have shown you. We have done, right? The important, it is because the turbulent flow is very complex one. It requires some more study to find out what the friction factor for turbulent flow is. So for that, we have seen a Moody's diagram, right? Here pipe roughness and water widely used for water distribution systems, oil, gas, pipelines and industrial process. And it is critical to calculate the energy efficient pipeline system design. It is very important to calculate the energy efficient pipeline systems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.